Hey, for today we'll do this problem. If uh, What is a direction field? Well, a direction field, you could say, uh, let's say there's a first order differential equation that we can't solve. Well, to approximate the answer or to draw how it looks like and get the derivative, we use direction field to know all these information. Second point, critical solution, how you get them. Well, critical solution, you set y prime to 0 to get the critical solution. And as for the equation we have today is y times y minus 1 times y minus 3. So I set that to 0. Okay, so and now I set all of them, all of the values to 0, and that's what I got. To look this as a graph point, I drew it here. It looked a little bad, but actually I also drew it on Desmos over here. Oh, my bad. Here, that's just better looking graph. You can see here, I put it in the x-axis instead. See the points? 0. That's when it hits. That's how you know it would be a critical point too. 0, 1, and 3. Okay, let's go back to our paper here. Now, we have to check the stability of the critical points. Well, I'd like to think of stability as, let me explain what stability is later. It'll be better if I show you what I think it would mean. See, our critical points here, I'll put it in a timeline, 0, 1, and 3. So to see between these critical points, which instant would be, at which range would be stable, I chose numbers between them. So before 0, I chose -1. After 0, 0.5 to 1. After 1, 2, and after 3, 4. As you can see here, this is the calculation. I just plug in the numbers I chose in the equation here, and this is the calculation for all of them. If I'll put a -1, I will get a negative, so I'll put a negative on top. And between 1 and 0, if I put it, I get a positive. That's why I put a plus over there. I get 0.625. 1 to 3, I get a -2. 3 and above, I get 12. So a positive, a negative, a positive, and a negative, and that helps me in drawing these arrows. That tells me which direction it's going. So if it's a negative, it's going to the left, and if it's a positive, it's going to the right. You might ask, why would that be so important? Well, that's how I would know which numbers are stable and which one are not. For example, look at 0. 0, the arrows are going away from it. That's why I think that's unstable. It's diverging away. And look at 3, it's the same thing. But then when you look at 1, it's converging toward it. That's how I would know 1 is convergent or stable, and 3 and 0 are not on the real graph. See, that's my direction field graph. The arrows are going away, and they're from 3 and from 0. But at 1, they're converging, and you can see here the graph on this app is the same as my graph. At 3, it's going away. At 1, it's conversion. And at 0, it's going away. And that's all it's saying here. T goes to infinity. T goes to infinity. At 3 is diversion. From T goes to 1, it's conversion. T goes to 0 is diversion. Now we go take a look at back here to prove what I'm saying here. See, I'll put a couple of solutions that would demonstrate what I mean. See, if a line was coming through 3, it would diverge away, just that I said. And also, I said C would be the same thing. See, my bad. I said 0 would be the same thing. It's C solution. See, it going through the arrow and then it went away. But if it's close to 1, it would converge toward it. Look, it goes close to 1 and then it converges toward it. What I think stability actually is, It's just whether it's convergent or divergent. Because if numbers keep getting close to the solution point, I think that's stable. And if numbers going away from the solution points or getting further from the solution points, that's divergent. And also the D to just showcase it could come from a three direction too. See, it's converging toward the one, and that just proves how this method over here works with the arrows. I just proved how this works in the graph.